thanks again, everybody who's online already. My name is Griffith Couser. I am a policy officer at the European Polar Board, which is a membership-based organization representing the polar programs of 30 different national research agencies, as well as some university and funding agencies across the European continent. And we're hosting this webinar in the SO-CHIC webinar series. The webinar is being recorded so that everyone knows. It will be available on the SO-CHIC YouTube channel. I'll post a link to that in the chat. And just as a very brief contextualization, the SO-CHIC is an EU-funded Horizon 2020 project focused on measuring and understanding heat and carbon exchanges between the atmosphere and the Southern Ocean. The project is aiming to add data and understanding to these processes, but we have JB here to dive in far deeper than I can into those details. But I will say the European Polar Board is the Work Package 8 lead, that is policy communication and dissemination. And as part of this, we have been conducting a webinar series on all of the SO-CHIC work packages. The last one, which was the final work package that we did, was work package 2 on January 12th of this year. Again, that's on the SO-CHIC YouTube channel if you care to look. And today is the final webinar in the series where we will hear from the project coordinator, Jean-Baptiste Sallée, on the project's work outcomes and desired future impacts. So questions can be asked at the end of Dr. Sallée's talk using the QA function, or you can ask them directly in the chat, I believe. For more info about the SO-CHIC project, I will post the link to the SO-CHIC website in the chat as well. So as a brief introduction, I will say Dr. Jean-Baptiste Sallée is the SO-CHIC Project Coordinator. He has a PhD from Toulouse University. He is a research scientist with CNRS, a research supervisor at the Sorbonne University in Paris, and was the lead author on the 6th IPCC Assessment Report chapter for ocean cryosphere and sea level. And I believe he has several more accolades up his sleeve, but I'll stop there and throw it to Jean-Baptiste.
Thank you very much, Griffith. So I'll share some slides. Can you see my slide, Griffith? Can you confirm that everything is okay?
It looks good.
Thanks. So yeah, thank you, Griffith, for this introduction, and thank you everyone for connecting to this final webinar. That's my great pleasure to give this seminar on the SO-CHIC project. So SO-CHIC, as Griffith already mentioned, it is a project funded by the European Union Horizon 2020 program. It started early or late 2019, early 2020, and SO-CHIC stands for Southern Ocean Carbon and Heat Impact on Climate. So what I'll do for this seminar, for this webinar, is first come back to an overview of why we should care about heat and carbon in the Southern Ocean. Basically give the motivation that brought us to propose this project to the European Commission, and introduce how we structure the project in terms of this work package and the vision of the project, and then go over some of the achievements that we did during this project. So the project comes to an end at the end of the year, so we still have a few months to go. But we are very close to the end. So let me start with this question of why we should care about heat and carbon in the Southern Ocean. So there are actually many ways to address that question. But here I'd like to take the angle of global climate. As you all know, I guess, Earth has been warming at a very rapid rate in the past century, unprecedented in the last 2,000 years. And what I want to discuss is that the Southern Ocean partly controls that rate, and therefore could change that rate in the future if Southern Ocean processes change in the future. So to try to address that question, or to try to convince you, I'd like you to consider this very simple linear Earth energy budget equation, which basically tells us that global warming depends on three main ingredients. The first one is radiative forcing. The second one is the heat that is removed from the atmosphere to be stored in the oceans. And the third ingredient is climate feedback, which modulates the energy that's stored on Earth. And climate feedback, they are mostly atmospheric things like formation of clouds and things like that. What I will try to convince you is that the Southern Ocean actually has a strong control on each of these three ingredients. For radiative forcing, of course, it depends on our emissions, but half of our emissions are actually stored in what we call natural carbon sink, and the ocean is one of these natural carbon sink. And so if we look, and therefore do control this natural carbon sink, the strengths of this carbon sink control radiative forcing. If we zoom on the ocean carbon sink, we realize that the Southern Ocean is actually a big player with approximately 40% of all the carbon that's been stored in the world ocean that entered through the Southern Ocean in the past 60 years. When we look at heat, the story is even more striking. 70% of all the heat that's been absorbed by the world oceans in the past 60 years has entered through the Southern Ocean. And when we look at climate feedback, I said that's mostly atmospheric things, but actually those feedback are controlled in some way by the temperature of the sea surface, and in particular, the temperature of the Southern Ocean, as illustrated by this figure here, which shows that the southern hemisphere cloud feedback depends on the temperature of the Southern Ocean. And therefore, that means that local processes that control stratification or the warming of the surface layer in the Southern Ocean do have a strong impact on climate feedback and therefore on global warming. So we have Southern Ocean having a strong control on each of the three ingredients and therefore on the rate of global warming. Now, why is the Southern Ocean so important for shaping a global climate response to human emissions? Basically, because it's a keystone of the global ocean circulation. That's nicely illustrated on the schematic of the global overturning circulation in a slightly distorted map called spillhouse projection, but which nicely places the Southern Ocean and Antarctic region at the center of the ocean circulation. Now, the Southern Ocean is rapidly changing, and so we can wonder how much of how many and how much of these processes can change in the future, and therefore change the role that play the Southern Ocean to shape global climate. We have deep ocean warming from the surface to the abyss. This ocean warming drive an ice mass loss of the ice sheet by melting the ice shelves around Antarctica that release fresh water at the surface of the ocean, which change the stratification, change the circulation, and therefore can impact all of the processes that I was mentioning before. We've got also change of the chemistry of the Southern Ocean with a strong acidification due to the uptake of carbon. So for all these reasons, SO-CHIC aims at understanding and quantifying the viability of heat and carbon budget in the Southern Ocean. So how do we do that? What did we propose to try to achieve that objective? Well, first, putting together a cool group of people. I've got only I missed many pictures here, but we basically put together a very nice group of scientists, about 50 to 60 scientists working on the project across 16 different institutes across 10 countries in Europe and South Africa for a total budget of 8 million euro. We had a timeline planned at the start of the project with field work mostly planned for 2021 and around 2021. But a few months after the project started, as you probably know, I guess, COVID broke through, and that's actually strongly impacted our project and in the fieldwork part of our project. And so we redesigned a little bit the timeline by spreading a bit the field work across 2021 to 2022 and early 2023 as well. And we also extended the project by a year, and so that the project will finish, as I already said, at the end of 2024, in a few months' time. The vision of the project was really to look at the key local processes occurring in the Southern Ocean and how they shape climate impact. And to do that, we designed a project with a combination of observations and numerical model, going from local processes with targeted experiments or very high resolution process-oriented simulations, and looking at climate impacts, long-term impact from long-term monitoring from observation, and a system model from the numerical model. We split the project in a number of work packages, a total of 8 work packages. The first work packages are dedicated to the study of key processes that we identified as important for heat and carbon storage. First work package focused on the air sea fluxes, the second and third work package on upper and bottom ocean ventilation, so how the climate signal, what it enter the sea surface, how it propagates in the deep interior, either by the surface or by the bottom. And also how the climate signal can be propagated to the deep interior by what we call abrupt shortcut events. So that's basically deep convection developing in ocean polynya. And that's the fourth work package. Then we've got 2 work packages focusing on the large-scale effect of these processes. Fifth work package is on atmospheric circulation, and the 6th on ocean heat and carbon changes in the Southern Ocean. And then we've got 2 work packages on project management, on data management, the 7th work package, and project management and dissemination, that's the 8th work package. And I'll say a word about those 2 work packages, which are mostly management work package, but actually key for the project, reaching out to our stakeholders. I'll say a word about those at the end of this talk. So the fieldwork mostly consisted in 6 operations, mostly focused on the Weddell Sea, spread, as I said already, from 2021 to 2023. And I've got a few pictures here of this work that we did, expeditions, a lot of work's been done. As you might know or not, but things don't always go to the plan, especially in the Southern Ocean. So we had a number of failures in the project, which we try to find alternative to still fill our objectives, and we did find alternatives to fill our objectives. So one of these failures was that we planned to use some sail drone quite far south in the subpolar Southern Ocean, but the sail drone could not sail as far south as planned, and so we had to redesign the deployment of these tools. We had a loss of a key instrument for us, which was the ASIP, basically measuring turbulence in the upper ocean. Unfortunately, we lost that instrument. We had to find an alternative measurements of microstructure turbulence, and we found that from surveyor gliders. We had the plan to deploy an eddy covariance mast on the icebreaker Argulas 2 to look at eddy covariance quite far in the subpolar seas. Unfortunately, for logistic reasons, that could not be done, so we had to redesign and find an alternative, and we mounted it on another ship, the Algoa. But that meant that we had to do this particular question experiment further north than expected. And finally, we deployed some moorings around mud rise to look at polynya opening processes. But for logistic reason and because of COVID impact, we could not recover those moorings on time for the project. We will recover them definitely, and we'll look at this, I guess, very interesting observation but that will be outside the framework of SO-CHIC after the end. So we had some challenges and failure, but we did find some alternative, and we also had a lot of success with a lot of different measurements that we made in the Southern Ocean. And yeah, I've got a picture of a few of these instruments, a lot of autonomous platforms, ship observations, and just some illustration of the very dense area of observation obtained around Modrise, which is a place where a large part of the project, or a part of the project, was focusing on to address the question of opening of polynia. In terms of numerical simulation plan, we had an ambitious plan as well, and almost everything's been done. Going from high resolution patch of idealized resolution patch of the ocean, going to Earth system model, to coupled model with a nest of high resolution ocean to look at how fine scale processes in the Weddell Sea can affect the couple system, and yeah. So I'll stop here with the overview of the project and the context motivation, and I'll go into some achievements that we made during the project. There's been actually many achievements, and I won't be exhaustive, of course. But I'll go over each of the work packages and give some example of the result that we obtain. So in terms of the first work package on RC fluxes, one of the first objectives was to really increase observation. And so, as already mentioned, we deploy a lot of instruments. I won't go again on that, but one example here of observation obtained is from a Carioca buoy that we deployed early 2021. That's basically measuring FCO2 in the ocean and FCO2 in the atmosphere. And this buoy has been drifting and sampling for more than a year, and therefore sampling in winter, where there is very rare observation of FCO2. And one interesting thing that you can already see here on this figure is that that's basically winter, and so we've got this buoy that measure FCO2 lower than FCO2 in the air. That means that there is no outgassing in this subpolar part of the Southern Ocean, and therefore intriguing, interesting, and we are currently looking at interpreting this data. That's a work done by Kirtan and Ag. But that's what, just to illustrate that one of the key objective was to fill observational gaps, and especially in winter. Again, to another example of one example of why we need to fill the observational gap, is here done in a nice figure by Mario Pema, where he basically gathered all the observation from the SO-CHIC database in the Weddell Sea on this map. That's the black and gray dots, and the number of observations per month is shown by this histogram. And what you can notice is that we really lack observation in winter. And so what Mario proposed to do is to use the measurements that we have of the carbonate system in the bottom water. The bottom water is formed, we know it, at the surface of the ocean at high latitude in winter, and therefore Mario proposed to use this DIC information of the bottom water to infer, trace back the PCO2 at the surface at high latitude in winter. And so that's what he did, as illustrated in this figure. You've got in black here the SO-CHIC observations, and the violet dots is inferred PCO2 observation in winter. So again, that was only to illustrate the challenge of data gaps, and how we try to manage to fill some of these gaps. There's been a lot of work in the first work package on trying to understand the processes that drive fluxes. And here I'm giving one example of the role of transient scale like storms in driving anomaly of fluxes of CO2 and heat. It was mostly done in two papers by Sarah Nicholson and Marcel Duplessis. And I'll give a few examples of the result done obtained by Sarah. So Sarah proposed to look at this particular question from autonomous platforms using a wave glider combined with a profiling glider just below it. And what Sarah found is that, that's here we've got a time series of delta P CO2, so basically the flux of CO2 at the sea surface, for a few weeks in January, February. And what you can notice is that you've got these outgassing events that are shaded in red, that are very transient. And Sarah proposed to try to understand what drive those outgassing events. And what she found is that many of those outgassing events are actually caused by high wind friction events, so storms, and the process that link the storm to the outgassing event is that the storm drive turbulence in the ocean, basically deepen the turbulent layer that's illustrated in this bottom panel here, where color show the turbulence intensity. Basically, brown means very turbulent, a lot of mixing. You've got on the y-axis the depth of the ocean on the top 200 meter, and the time series on the x-axis. And so you've got, when you've got this storm event shown by the black triangles here, you see that there is a deepening of the turbulent layer, which deepens so much that it reaches a layer of the ocean that's very rich in carbon, and therefore entrain that carbon to the surface and outgas it in the atmosphere. So we see that this transient event that we often don't resolve or miss in our observations might actually be key for these fluxes of CO2 and also heat, actually. Another process that we looked into in the first work package is the role of the diurnal warm layer, or what we call the diurnal warm layer, on the magnitude of the CO2 flux. And the motivation to look at this question was this study by Dong et al. 2022, which basically said that the global uptake of CO2 could be strongly modulated by up to 30% if we account for what we call the cool skin effect. And so we designed an experiment to look in particular at that question, and where we have a ship here with an ISAR, so measurements of temperature of the sea surface, really looking at the skin temperature. We've got a flux tower as well, and we've got a glider just below the ship with a wave glider next to it. And so that setup allowed basically to look at this particular question and to infer the impact of cool skin on the flux of CO2. So here's an example of the result from this experiment. So we've got in gray here the skin temperature measured by ISAR from the ship. The orange line is the sea surface temperature that we basically obtain from a thermosalinograph. So that's the classical way to obtain the sea surface temperature. And you see that you've got a big difference between the skin temperature and what we measure from the ship, which is basically at 5 meters. So it's very close to the surface, but that's not the skin. With a development of, and sorry, I didn't say it, but that's the gray shaded bars are night. So we've got a few day time series here. The y-axis is temperature. Yeah, that's a summary of that time series for 1 day. So you see that you've got a development of a warm layer during daytime, which you don't really see when you take water at 5 meters. And when you account for this warm layer, when you correct for thermal bias, that actually impact the flux of CO2. And our estimate is that it's about a reduction of 12% in the mean flux of CO2 because of this effect. So important to take into account. So I'll now switch to second work package on the upper ocean ventilation and turbulence. So we started this work package by looking at long-term changes to give the context of give the context. And so what we did in this study is to look back at all the observation that we could gather from in the world ocean. Actually, we did a global study to look at the specificity of the Southern Ocean. And so we we took all the temperature salinity profile that we could get and looked at the change of the stratification just below the mixed layer. And we did that in summer because we've got more historical observations. And when I say the change, that the change over the last 50 years. And what we obtain, what's shown on this map, is the change over the last 50 years in a square second per decade. And basically, when you see red, that's because you've got that means that you've got an increase of the stratification just below the mixed layer. And so basically, we see a strong increase of the stratification globally. It might seem that we've got weaker stratification increase in the Southern Ocean, but that's because the background stratification in the Southern Ocean is much weaker than the rest of the world. But if you look at the percentage change, so the change divided by the background stratification, the climatological stratification, you find that there is in the Southern Ocean 8% by decade change. So very strong change of the stratification in the Southern Ocean, very rapid stratification increase. We looked at what drives this stratification increase, and that's these two plots here, where that shows the percentage contribution to the stratification trend from the temperature on the left and from the salinity on the right. And in the world ocean in general, that's really the temperature, the increase of the surface temperature that increased the stratification. But in the Southern Ocean, and in particular in the superpolar Southern Ocean, we see that the story is a little bit different. That's really the salinity that has a very strong contribution to this stratification trend in this part of the world. And we also looked at the change of the mixed layer depth, and we found a surprising result that the mixed layer depth has been deepening in the past 5 decades at a rate of about 3% per decade. That's surprising because we've got an increased stratification, so it's harder to basically mix the ocean, but we do have deeper mixing layer at the surface, and that's because basically we've got an increase of stratification, but we also have an increase of the winds and wind gusts, which increase the turbulence in the surface layer, and that's been winning over the past 5 decades. And those two change, stratification and deepening of the mixed layer, impact ventilation. Both impact ventilation, as nicely discussed in this paper by Lapiana Patar. So that motivated us really to try to better understand those turbulent processes, because those that drive this deepening of the mixed layer, the link between the wind gusts, the turbulence source, and the deepening of the mixed layer. And so that was one main objective of this second work package, to understand these turbulent processes in the mixed layer. And we decided to do that from a survey of gliders. But before going at sea with our gliders, we wanted to have some understanding of how we should sample, what is the impact of our sampling. And so we designed a numerical simulation experiment. That's the work from Ryan Patmore, which basically did a idealized high-resolution patch of the ocean, in which he did sample virtual glider paths to test the impact of our sampling strategy on the question we ask. So one thing we are very interested in is the resolution of the horizontal buoyancy gradient in the mixed layer, because they drive a lot of the turbulence. And so Ryan here did some tested the different sampling strategy with different lengths of the observation, from 1 week to 3.5 months, and with a different number of gliders, from 1 to 20 gliders. And that's the result here. So he basically plotted the distribution of buoyancy gradients that we would recover from these different observation strategy. That's the color here. In the truth, the model truth is shown in orange, the orange line here. And so what the bottom line of this story by Ryan is that with one glider and 1 week sampling, it's very hard to constrain the orbital buoyancy gradients distribution. But with a few weeks observation and with something like 4 gliders, you start to constrain a much better the distribution. And so that study basically informed us on how to design our observational strategy, and we did that. There's been a lot of communication between the modelers and the observationalists in this work package, and we actually went at sea with 4 gliders for a few weeks time, even a few months. And we did sample a little bit like in the model with butterfly pattern in the sound machine. And there's been a lot of data acquired from this observation of glider observations. Here I'll just show very quickly one plot which shows the deployment of a few months from 2 gliders. And the bottom panel shows the wind friction, and the upper panel shows the wind frictions, and the bottom panel shows the mixed layer depth. And here I just want to highlight, because of time constraint, I'll just focus on one easy things to look at from this plot is the fact that when you've got strong wind frictions, so storms, you've got a deepening of the mixed layer that echo a little bit the result of Sarah. And as soon as you've got calm days, very rapidly you've got restratification of the mixed layer, which will impact development of turbulence in the mixed layer. We also, from those glider paths, not the same deployment, but from glider as well, looked at the impact of other processes like sea ice, meltwater, and there's this nice paper by Isabelle Guidi that shows how sea ice, meltwater enhance submesoscale front and therefore affect the buoyancy flux. The buoyancy flux at the sea surface. That's one from the glider. We can only see something very zoomed in, and so we wanted to have a wider look at how mesoscale or submesoscale could impact the ocean on a wider scale. And so we worked together with Mati Soji to develop a new satellite product that could resolve mesoscale activity in the CI sector. So on the left, you've got a conventional altimetry product, which basically you are completely blind in the CI sector. We don't see anything. And Mathis worked with space agencies to recover observation in cracks and leads in sea ice, to recover observation of sea surface of sea level anomaly in this sector. And with a number of different satellites, you could have relatively high resolution and look at mesoscale activity in the sea sector. That's what he did. Yeah, we've got a movie of all these AD cores that are captured from this altimetry product. And one of the results that he obtained is to look at the impact of sea ice concentration on the eddy amplitude. So on the y-axis, you've got eddy amplitude. X-axis is the sea ice concentration. Let's look only at the black curve, which shows the mean eddy amplitude in these different sea ice concentration. For this different sea ice concentration, and what the striking result here on this figure is that as soon as you enter a concentrated sea ice, so back ice, you the edge amplitude decrease rapidly, and so the sea ice act really as an eddy killer. Another interesting aspect in this figure is that in the marginalized zone for concentration between, let's say, 10 to 50, you've got an increase of the eddy amplitude, and that's because we think of this effect of meltwater and also the effect on of the stress divergence in the marginalized zone. So let's switch now to the third work package on bottom water. One important aspect of this work package was to do a synthesis of the observation we have in this part of the world. There's a number of nations, especially in Europe, that developed over the years observational strategy in the Weddell Sea. And the work package really was very powerful. The work of the work package was very powerful by putting together all these different observations, and that's one of the results of putting all this observation together is shown in this work by Zhenqi Zhu, which was able to show that the Weddell Sea is losing its bottom water at a rapid rate, about 30% volume loss in 30 years. And Zhenqi was able to link that reduction to a sea ice anomaly in the formation region in the southern Weddell Sea. Basically, you've got climate modes anomaly that drive winds that compact sea ice in the southern Weddell Sea, which basically close the polynya, reduce the dense shelf water formations, and down the line you've got less bottom water in the Weddell Sea. Pedro Lanino looked also at bottom water from other moorings in the Antarctic Peninsula, a set of moorings with a long historical observation, and what he found is basically echo some of the Zhenqi's results in terms of the importance of climate modes. Where Pedro really highlighted the importance of climate modes for modulating the density of bottom water formed, the volume and the transport, density, volume, and transport of bottom water from in this part of the world. We next looked another aspect that I'm really mentioned the bottom water formation and export. But another part that of interest for this work package was the consumption of bottom water, and that was tackled by the work by Tim Holzer and Casimir Delaverne, where they found from an inverse model using green functions that's much further down the line. That's the consumption of bottom water in the Pacific abyssal zone, where they found that diffusive transport, which is distinct from overturning transport, are really the leading control for the Pacific consumption of bottom water, and therefore nutrient and carbon storage. Based on that work and other work, Casimir really focused on trying to better represent diffusive mixing in global model. That was one important aspect of this work package to improve our global cost resolution modeling in terms of representing those export and consumption of bottom water. And so there's been a lot of work dedicated to that. And we reach a point where we've got one global cost resolution model that do reproduce nicely the regions of dense shelf water formation region. So on the left is the observation of bottom density from observations. On the right is the same, but from this model after calibration. And you see many differences, of course, but you also see some things that are done pretty well in the model with these four regions of production of dense shelf water, very dense water, which are exported in a similar fashion than in the observation. the bottom density is much lighter because there is spurious mixing that's very difficult to represent the overflow in those coarse resolution model, but still the formation of the dense water in terms of the regions and the export are done in a fairly realistic way. So now switching to the fourth work package. We started this work package by trying to have a look at how climate model represent those open ocean polynya. And that's a paper published by Martin Morman. And basically you've got a lot of different responses. Each model does basically its own things, with some model doing better job than other. But really, there is a need for better understanding the processes that control those polynya and to better understand what is required in terms of process representation for improving the representation of this polynya in coarse climate model. And so the first part of this work package was really focusing on what trigger the recent motorized polynya that we observed in 2017 and 2016 as well, I think. And so we focused on two aspects. The first is the trigger from the surface ocean, and the second is the trigger from the subsurface ocean. So in terms of the surface ocean, Aditya Narayan published this very nice paper, and I'm only showing the synthesis schematic of his paper. But basically, what he found is that the reason why we had this, not the only reason, but one important preconditioning, let's say it like that. One important preconditioning of the opening of the polynya in 2017 was that you had surface stress that were more eastward, and therefore you've got an anomaly effectment transporting salinity directly north of the Taylor cap. The Taylor cap is basically on top of motorized. And so as you transport salinity on the northern edge of motorized, you precondition the water column for destabilization, deep convection, and that allow to precondition for the opening of the polynya in 2017. In terms of subsurface, we also had the preconditioning. That's another work that was done by Aditya, where I looked at ocean analysis to look at the freshwater content of the circular deep water, so the water that's directly below the surface layer in this part of the world. And so on this plot, you've got the salinity of 2014 that's shown here, and the anomaly from the 2014 year is shown in all other panels. So for 2013, 2015, 2016, 2017, 2018. And what Aditya found is that in 2017, you've got an advection of freshwater. So sorry, motorized is this black contour here. So that's the region we are interested in particular. And so in 2017, you've got an advection of freshwater that wrap around motorized and that fill the Taylor cap. And that this advection of freshwater basically precondition the subsurface for the generation of deep convection. So you've got both preconditioning of the surface with more salty water, preconditioning of the subsurface with fresher water than usual, and so that allows for easier generation of deep convection. We next work on as I said, the requirement for representation of this polynya in model, and so that's one work from Birte Gulk, where she tested different parameterization scheme to test whether they would help develop this polynya in a numerical simulation. And so you've got a number of different panels here, but basically you've got the classical parameterization that's shown in this panel and some other parameterization based on edematous flux. Let's not enter into the details, but that's another type of parameterization, less classical. That and you've got different version of it in this different panel, and basically the bottom line is that this kind of parameterization helps having a better, more realistic development of polynomial in this particular model, and that could be an interesting way forward to better represent this polynomial in numerical model. We the last part of this work package was to look at the impact of modularize and polynomial, and so we did that looking at different aspects. Here I'm showing one example of a work done by Nathan Steiger on the impact of the modularize, so the ride itself, but not the convection, but really the presence of the rise on the development of chlorophyll bloom. And what Nathan found is that, with our colleagues, is that there is a development of a halo of high chlorophyll bloom around modularize that develop almost every year, not every year, but almost every year. You've got this halo of high chlorophyll, and she linked that to the presence of circular deep water very close to the surface that mix up to the surface and that recharge nutrients to the surface. So you and that cause very large bloom of chlorophyll, and therefore that has an impact on the carbon storage. We wanted to look at the impact of polynomial event on the larger scale circulation, or to test whether there would be an impact or not. And so we look back. We took again this new satellite altimetry product that was produced by Mathieu Sauger. And we looked at the circulation in the Weddell Sea, and so that's basically here a time series of the first UF mode of the sea level anomaly in that's the entire circular sector here, but that's really dominated by the Weddell Sea. And so you see a nice seasonal cycle. That's the blue line. And this seasonal cycle is really dominated by the seasonal cycle of wind stress curl, which drive basically an intensification of the Weddell gyre in winter. And so I'm mentioning a seasonal cycle because if we wanted to look at the anomaly during the polynomial, we needed to remove that seasonal cycle. And so that's what we did, looking at higher modes of the sea level anomaly, and clearly we see some anomaly in 2016, 2017 during the polynomial event, and so some potential association relationship between anomaly in the large scale circulation and the opening of the polynomial. So I'm now switching to the fifth work package on the impact of atmospheric of these processes on atmospheric circulation. For this work, led by Oli Harris, we used atmospheric only GCM, to which we tested we tested the impact on those models of the presence of a polynomial. So we have a mask, sea surface temperature mask, basically, where we have this fingerprint of the polynomial, which we either put or not put, and we look at the response, or they looked at the response on the large scale atmosphere. Oli did that with 3 different models with a per resolution each time. And the result of our work is shown here. So for each of the 3 models, for 3 quantities: near surface temperature, sea level pressure, precipitation. And on this figure is shown the impact of the presence of a polynomial. And so the bottom line of this work is that the response of the polynomial is very localized. It's confined to the boundary layer. It doesn't go very high in the atmosphere. There is no remote response away from the polynomial. And it's slightly stronger at high resolution, but still it doesn't have a large scale effect. So we were quite surprised by this result because it does contradict previous literature, but our understanding is that previous literature based their study on climate model, which usually have way too large polynya, and so the impact of their very large polynya might be overestimated compared when you do it with a more realistic polynya size. And here we use the polynya size of the Weddell polynya of the 70s, which was very large compared to the recent polynya that we observed. The second aspect of this work package was to go a bit further and to look at how small-scale processes in general in the Weddell Sea would affect large-scale circulation, and how the couple effect could play a role there. So what we did for this, or what Malin did for this part of the work, is to use a couple model in which she nested a high resolution ocean of tenths of a degree. And then she ran experiment where she looked at the impact of 4 times CO2 experiments without the nest and with the nest. And she looked at, I'm showing here just a snapshot of some of our results, looking at the mean zonal wind strengths. What Malin shows is without the nest, you've got, with climate change, or with 4 times CO2, you've got an increase of the extratropical jet, and which is slightly stronger in summer than in winter. And when you start having the nest, this increase actually is similar in summer, but it's very different in winter, with a shift equatorward in October, November. And so what she concluded that this is the sea ice loss effect dominates over the mean response to global warming. Yeah. Now switching to the 6th work package. So focusing on the heat and carbon change, one first question that was tackled in this work package was to try to decompose the impact of different fluxes on the heat storage in the Southern Ocean. And so that's the work that was led by Mark Hag. And so what he did is running factorial experiments where he only so that's done with simulation where you apply only one flux each time, and so that's you look at the role of wind variability here, air sea flux variability, and net freshwater forcing here. And so you run that and look at this impact for heat storage. And here is the schematic of his concluding of his conclusions, and I'll focus on the Weddell Sea since we already talked quite a bit on the Weddell Sea during this talk. So his conclusion is that the weakening of the coastal easterlies wind caused, so the wind effect caused a reduction of the strength of the slope current and therefore a warming of the region. But on top of that, you also have a change in sea ice related freshwater flux, which itself strengthens the slope current and therefore reduce the supply of warm circular deep water into the Weddell Sea and therefore lead to a cooling. And so you've got the superposition of these two effects, which basically lead to moderate level of warming in this region. But because you've got counteracting effect because of the different fluxes. Another work that led by Mark was to look at the difference between the pattern of excess heat and excess carbon in the past decade. So you've got here those patterns vertically integrated or zonally integrated. And what Mark noticed is that these trends are spatially anti-correlated. And so he tried to work on the cause and question what are the causes. And that's basically because of redistribution effect, which dominate for excess heat while the uptake of anthropogenic carbon dominates for excess carbon. So we've got different processes here at play. And finally, a work done by led by Linus Vogt, where he looked at how much the increased future ocean heat uptake could be constrained by the state of the Southern Ocean. And so that's he found some very interesting result by looking at SO-CHIC model ensemble. So we've got here on this plot so each black dot is a different SO-CHIC model. And the y-axis is the ocean heat uptake until the end of the century for one scenario, 585. And on the x-axis, that's the Antarctic sea ice extent baseline. And you see a very nice correlation, a very high correlation between the Antarctic sea ice extent and the ocean heat uptake in the future. And the reason why we've got such a nice correlation is because the Antarctic sea ice extent is a fingerprint of how strong will be the change of the Southern Ocean in the future. When you've got a lot of sea ice, it will basically shrink to zero. And so you will have a very rapid change in the Southern state, which will affect cloud feedback, sea surface temperature and cloud feedback. That's what's shown here. That's now the pre-industrial sea ice extent on this plot and on this plot, and correlated with the SST of in the Southern Hemisphere and cloud feedback, global cloud feedback. And so when you've got a lot of Antarctic sea ice, you rapidly change your Southern state in the future, which impact the temperature of the Southern Ocean, which impact cloud feedback, and therefore impact ocean heat uptake. And so with this very nice correlation, we are able to constrain future ocean heat uptake because we know we have observation of Antarctic sea ice in the historical period. And so we are able to constrain future ocean heat uptake. And the conclusion is that we should expect a larger future ocean heat uptake than what tells us the SO-CHIC ensemble unweighted. So I'll finish quickly by mentioning the 7th and 8th work package on data management and dissemination. As I already mentioned at the start of this talk, very important work packages to reach out to our stakeholders. I'll be quick here because of time. I think I'm a bit lengthy here. But there's been a lot of work on the 7th work package on data management, a lot of support for the project. And one of the achievements of this work package is to really build an integrated data system, and that actually ultimately led to the support of the Southern Ocean Observation System map. And we are very proud as SO-CHIC to have contributed to this community effort. And this SUS map that SO-CHIC contributed to largely has been noticed as one of the most important deliverables for the Southern Ocean Observation System community. So at the last SUS symposium last year. So a lot of amazing work from the data management of SO-CHIC that have a legacy through Southern Ocean Observation System. In terms of the dissemination, amazing work done by the European Polar Board, Griffith, Eva here today. I'm only mentioning 3 activities, but there's way more than that they've been doing to reach out to different stakeholders, policy briefing, presentation and panel discussion at different events like AG, USCAR, and of course this webinar series, which have been great to either contribute or listen to. And which I'm basically concluding now with this last slide. So I'll be very brief for the conclusion, but I'm happy to take any question and discuss with you. So in conclusion, we had very productive group, very nice group also to work together, tackling key processes collectively. That really made a nice step toward better understanding of the South Nation with new observation and process understanding. And we still have a few months to go. There's still a bit of work that we need to do. I think in particular synthesis work and also prepare for the next adventure. So I'll stop here and take any question. Thank you.
Thank you very much, Jean-Baptiste. That was not really over time. I think we still have plenty of time for questions. So I would encourage the audience to use the Q&A feature to ask any questions they might have. I think you could also put them in the chat if that makes things easier. And while people are thinking, I'm going to give you a question here, which I am not a natural scientist, so call me out of my element here. But the European Polar Board co-coordinates the EU Polar Cluster, of which SO-CHIC is a member. And I just wanted to know from your perspective where you saw the strongest links between SO-CHIC and some of the other EU Polar Cluster projects, whether the other projects have impacted SO-CHIC's work, or what are some of the best synergies? Where do you think that those links might be improved or strengthened in the future?
Yeah, so first, thank you for mentioning the European Polar Cluster, which is a very nice tool, I would say, for communication, dissemination, reaching out, putting force together. I think that's a very nice tool that exists. In terms of linkages with other projects, I would say that we had natural linkages with some of the project because of basically partners shared across different projects like GPAX, which ended early last year, I think. That really looked into interaction of ocean and ice shelves, and we didn't do too much of that in SO-CHIC. So that was it was basically the southern boundary was the continental shelf of Antarctica, and GPAX, the northern boundary was the continental shelf. So that was a nice merging there in terms of scientific objective. And the other project where we've got quite a lot of collaboration is the project that started last year called Ocean Ice, which I would say is very close in terms of consortium. That's a sister project with SO-CHIC, where we've got a lot of nice collaboration where Ocean Ice really start from some of our work. Yeah. I don't know if that's fully answer your question, but
I think it does a good job. The Polar Cluster is quite a large group of projects, so it's hard to narrow it down too much in terms of linkages and everything like that. But thank you for the answer. There's a question in the chat here from Simona Arakri asking, what standard for metadata prior publication did you use? And I think Antonio Novellino was on here, but I think we just lost him. So that one goes straight to you.
That would be very helpful to have Antonio. So
Yeah.
Antonio Novellino was the lead of, or is the lead of the WP7 in SO-CHIC. So the work package dedicated to data management. And I must say, I can answer this question. I'm not sure. I'm not sure. I don't know. Antonio would be able to answer, I'm sure, but I'm not the right person for that.
Yeah. Sorry, Simona. If you send us an email, we can definitely put you in touch with the right person for that.
Yeah, definitely. Yeah, it'd be a
Yeah.
pleasure.
Any other audience questions out there? Otherwise, I'm going to ask another one, and I'm a policy officer, so fair warning. I'm going to say So as a European uh, who is geographically very far away from the Antarctic, what do you think this project's impact should be on policymaking in the EU? How do we get less scientifically literate people to understand the data that you've collected, the project conclusions, things like that? How do we get the Southern Ocean a bit further up on the priority list?
Yeah, so I guess well, there's definitely many different angles that could be tried. I don't think if there is one good response to this question, but maybe one aspect is to communicate or better communicate maybe on the fact that Southern Ocean really has global impact and does have a strong impact on our climate in Europe. And I think the last slide that was maybe a bit too complex for reaching out to a policymaker, but that's basically that tells us that the processes that are ongoing in the Southern Ocean do have an impact on global warming, on the level of global warming. And there's a number of papers coming out lately on the impact of the processes of the Southern Ocean, the warming of the Southern Ocean for the timing of what we reach a global warming target like Paris Agreement, what's ongoing in the Southern Ocean, the rapidity at which we warm the surface layer of the Southern Ocean, the change that we are currently seeing with Antarctic sea ice loss, which have a strong impact on sea surface temperature, do have a strong impact on the level of warming. There's feedback processes that are ongoing, that are put in place, or that might be even maybe too confidential. There's plenty of knowledge gaps still, but that we think have the capacity to strongly change global warming. So for that, I think that's one impact. The other one, of course, which was less the focus of SO-CHIC, but that's sea level, of course, with the Antarctic contribution to sea level.
Yeah, just going off of your comment there on data gaps, what do you think are the most important data gaps that are still left after SO-CHIC? Are there any that you should have filled but didn't manage to? Are there any that you discovered along the way?
Yeah, maybe I will talk about knowledge gap more than data gaps, even if they are linked. I would say that, well, of course, there's plenty that's left. We didn't fill all the Southern Ocean knowledge, but I would say that there's many of these knowledge gap in the Southern Ocean, in our understanding of the Southern Ocean. I would say that the most pressing, to my view, and I'm happy to be contradicted or happy to discuss. But I would say that, to my view, the most important one are this the interaction between ocean and ice shelves and ice sheet in particular. There's plenty of data gap there first, and also knowledge gap in general. How things are changing, how things are interacting, to be broad, that covers plenty of scientific questions. And the other one is all the feedback between the ocean and the atmosphere, the ocean and the ice sheet, ocean and sea ice, which might, we think there's plenty of suggestion there, might amplify global climate change. And there's plenty of knowledge gaps around those feedbacks and those potentially amplifying feedback.
Yeah, I'm reminded of the work of Work Package 1, which was talking about CO2 fluxes driven by storms. And this is just maybe as an example. Do you find that that could be sort of a reinforcing cycle of storms getting worse and releasing more CO2 into the atmosphere? Do you have any other sort of processes like that that were discovered, or would you consider that to be similar to a tipping point?
No, I wouldn't go that far, but I think we so I think that work from Sarah and also from other partners um, is very interesting and also pose a big challenges, because that's very hard to if we need to observe in every storms, then we've got a big problem. Um, so I think so I think the next step after this work is really to try to have a better understanding of the net effects of these processes on the net flux. And then we don't have a clear. So there's in Sarah's paper, a very nice paper, she did some estimate of that. But I think we still need to have a better estimate of the net effect of these processes. That it's seasonal, this seasonal cycle that was only in summer that might be different in winter. And yeah. And then when we have an understanding of net effect, we can maybe discuss what it means in terms of future change with the gust of winds becoming more intense and things like that. But there's this first step that we miss first. Yeah.
Okay. Just sort of similar to that, how much is the project contributing to the IPCC seventh assessment or general work there? Do you have some sense of the publications that are going into that or the interactions?
Yeah, so the project started in 2020, I think. Yeah, early 2020, and the deadline for um, for publication to enter the IPCC report was summer 2021. So we had only 1 year to be able to publish, but there's a number of SO-CHIC publication that was cited in the IPCC report. But not all, of course, because of this publication deadline. I think the impact of SO-CHIC will be, I'm only guessing, I don't know, will be stronger in the next assessment report in the coming years.
All right, thank you. Simona is asking about the paper on CO2 fluxes related to wind gusts. Is that available on the SO-CHIC website? Do you happen to know?
I guess so, but I can definitely post it in the chat. I would think that it's on the website.
I think it is. It should be.
I will post it now. Yeah. We can.
Thank you. Does anyone else have any last minute questions? This is the final webinar in the webinar series, so this is sort of a last chance to get Jean-Baptiste sitting here face to face, as it were. Otherwise, I'm going to wrap up, I think, pretty soon. And before I wrap up, I'm going to ask sort of a half question. If you can, yeah, Andrew just beat me to it. So the summer school coming up in Corsica is going to feature a bunch of early career researchers, and I wonder if you could share any of the goals of that, and just if you could expand a little bit on ECR contributions to the project in general that you've seen, and what tools you think are most useful for ECRs to get out of this.
Yeah, so in terms of ECR contribution was of course as in many of these projects fundamental. In terms of the tools that are useful for ECR, maybe we should ask ECR and whether and we should definitely do it as we end the project to have a feedback from the ECR and what could be done better, what was done well. In terms of the walking through the project. So now switching to the summer school. So the summer school, we decided to organize a summer school at the end of the last year of the project because we had the opportunity to do so, and really to give the to form the next generation, to have some sort of knowledge passation across the different. We have basically this nice consortium of world experts on this specific subject, and we thought that would be nice as a legacy of the project to have this 10-day discussion summer school formation of early career scientists. So we will do that in a few weeks from now, next month, in May in Corsica. And yeah, I'm not sure what to tell exactly about, but the summer school will focused on so we designed it really to be first international, so it's wider than SO-CHIC. It's funded mostly by SO-CHIC, but also by other projects like Ocean Ice. And that's the contributor, the panelists are not the lecturer are not only from this consortium, and the students are not only from this consortium. And yeah, thank you for posting the link. And we designed the program to be really interdisciplinary, so focusing on Southern Ocean physics, climate, of course, but also on interactions between ocean and ice sheet, ocean and sea ice, marine biology, and also going to governance, policy relevance of the Southern Ocean. So to try to have an holistic view of the Southern Ocean.
Thanks very much. Yeah, the European Polar Board will be doing the policy and governance section of that, so it's a little shameless self-promotion there. I think let's wrap it up unless anyone wants to pitch another question, but I think we're about done on time here. So I would like to thank all of our audience, all of our participants, and especially to Dr. Jean-Baptiste Sallée for the talk and for the questions and for the discussion. I want to thank Eva Horochakova for her work promoting the event. Also to my predecessor, Joseph Nolan, who started this series way back towards the beginning of the project. So you'll see his face if you go through the previous videos. And of course, to the entire EPB Secretariat for their support. A recording of this event will be available shortly on the SO-CHIC YouTube channel. And as this is our final webinar, I'd like to also give a special shout out to Jean-Baptiste and his organizing team for all of the support during the project and for what I would say is a quite successful project overall. It's not quite over yet, but we're getting towards the end. So thanks everyone. And I would say see you later, but this is our last one. So thanks everyone, and I hope it's been useful.
And thank you very much to the EPB in general and to you, Griffith, for organizing this webinar series.
Yeah, well, it's our pleasure. So thanks again, and talk to you later. Bye.
Bye.